Hey everyone, welcome to the Big Proof program. We'll start with a round of introductions. So my name is Shankar. I go by one name, so ignore the first name, just the last name. I'm from SRI International, and we'll start from here and work our way through this.
I'm Fabian from Technical University of Munich.
Christoph Wintersteiger, working for Microsoft Research.
Vladimir Voyevodsky from the Institute for Advanced Study in Princeton.
Marie-Françoise Roy from Rennes University in France.
Lars Peters from Aarhus University.
Jeremy Appigat, Carnegie Mellon.
Mike Gordon from here.
I'm Andy Pitts. I'm a local from here.
Georges Montier from INRIA in France.
Paige North from here.
Bert Rijke from Carnegie Mellon University.
Peter Lefny-Lamstein from the University of Stockholm.
Benedict Ahrens from INRIA.
Floris van Doorn from Carnegie Mellon University. Steve Audi from Carnegie Mellon University.
Ian Alton from here.
Chaitanya Mangla from here. Eric Traber from here.
Okay, nice to have a lot of locals out here. So greetings everyone. So this presentation is going to be quite informal. It's just to get us acquainted and get some idea on the kinds of things people would like to do during the Big Proof program out here. So I'll start off by actually doing a card trick, just to break some ice, okay, and then we'll work our way from there. So in this card trick, actually, I have a deck of cards that's arranged as spades, hearts, clubs, diamonds, spades, hearts, clubs, diamonds, spades, hearts, clubs, diamonds, spades, hearts, clubs, diamonds. Okay, and so Floris, at some point, tell me to stop. Stop. So then, we take these two decks that we've created, and remember, you told me when to stop, and so we're going to riffle shuffle them. Okay, so there's a riffle shuffle. So here we go. So I mixed up the cards, correct? And so I'm going to basically take them off 4 by 4, and you can check that they form a match set. Okay, in spite of my riffle shuffle, that is, there'll be one of each suit in it. Okay, so Andy, you will be my judge. So is that a match set?
It is.
Okay, so
I'm still wearing my watch.
is that a match set?
My God, it is.
Is that a match set?
No. Oh, yes, it is.
This
has to be,
yes.
yes.
Yeah, okay.
It is, yeah.
Okay, so good. It's the power of mathematics that it's always worked. It's never actually failed to work out. And I notice I don't even have to look at it. I don't have to check that. Even looking at the dark side of those cards, I know that they're match set. Okay, so somehow out there in this black box version of it, I have my secret. I know that it's matched. Okay, so let's see. I can try and use this if I know how.
I thought you were going to show us a proof now.
I want you to spend the rest of the talk thinking about it. So it is quite an interesting thing to prove. So and as Bas actually asked right away, this is something that you expect. You demand to see proof. And as Dedekind did in Science, nothing capable of proof ought to be accepted without proof. And indeed, all of this magic stuff you should accept only with proof. And one of the things that happened in the last 100 years is that people started to formalize things a lot more precisely. That is, they didn't just take axioms that were stated informally. They actually started to put things into symbols. The symbols carried a very specific meaning, and this led to a kind of greater precision. So the Gödel's quote, the development of mathematics toward greater precision has led, as is well known, to the formalization of large tracts of it, so one can prove any theorem using nothing but a few mechanical rules. Well, he makes it look easy, but it is true that with nothing but a few mechanical rules, you can actually derive vast tracts of mathematics. And I think part of the thing that we'd like to achieve in this is that we bring a kind of pragmatic flavor to it, so that in practice, not just in principle, people are actually formalizing mathematics and building up this edifice. So when computers actually came into existence, people naturally looked at proof checking as one of the interesting things to do. And John McCarthy was one of the pioneers in this, and this quote, checking mathematical proofs is potentially one of the most interesting and useful applications of automatic computers. Is something that he said, I think, in the early 1960s already. And one thing with computers is that we can use them as a kind of way to experiment with ideas, with formalizations and so on. And previously you may have had a theory that was something that you weren't sure was predictive or not. You couldn't operationalize it in any way. But with computers, you can actually start to write code. And so this is the quote due to science is what we understand well enough to explain to a computer. Art is everything else we do. So this should be the case with mathematics, that we should be trying to explain mathematics to a computer more as a way of ourselves gaining some understanding about it. So when I'm sitting there and trying to formalize a proof, I'm not making the computer more or less smart. I am actually debugging my own mind. And there are lots of mistakes that I make that if I didn't have access to something that would check my reasoning carefully, they would kind of sit there unchecked. So to me, mathematics is this science of pure abstraction. So you talk about things like maps and graphs and algebras and sequences and so on. Mathematical structures that are just pure abstraction. You don't have to worry about whether they exist or not in order to find them interesting to study. That's somebody else's problem. And it turns out that many of these abstractions have been unreasonably effective. For most of the abstractions that we can think of, they do have some concrete instantiation in reality somewhere or the other, perhaps in some other abstraction. So it turns out to be useful. But when you're thinking about pure abstraction, you don't have an experimental way of checking whether something holds or not. So proof is the way that you actually find to sort out which claims about abstractions hold and which ones don't. In particular, with the formalization of proof, you can actually reduce it to a small number of principles, so that if your abstraction is defined with these axioms, say, then you can say that these consequences of it follow for any instance of those abstractions. So having the axioms and inference rules makes it possible to actually build a body of knowledge that you can trust. And with these tools like proof assistance, decision procedures, theorem provers, we can actually start to build formal proofs at scale. And the main hope that we have with the Big Proof program is that we are able to advance the technology to a point where serious mathematicians are actually using it to derive new results. That perhaps this is a way that we can get around the challenge of refereeing mathematical papers that are hundreds and 1,000 pages long and so on. So we can actually say that we've built up a body of knowledge. So this makes it easy for you to actually review your results. And it's not just enough to say that the result is valid or not. I mean, this is a kind of a repository of knowledge that we can try variations on proofs. We can take an existing proof and perhaps simplify it. We could extract out exactly the principles that we depend on. We could do reverse mathematics with it. We could say that, yeah, these principles you absolutely need in order to derive this particular result. And eventually, the thing that's been happening is that the watermark for mathematics has been expanding. So more and more fields are getting mathematized. And we hope that, educators will find this technology useful in communicating mathematics to students. Students will themselves use it the way they use video games, for instance, to actually learn and understand mathematical ideas. So, the story starts with Thales, who seems to have been the first person to think in terms of proofs. And so he was also the person who tried to explain a multitude of phenomena from a small number of hypotheses. And so Pythagoras was the one who said, we should study mathematics for its own sake. I mean, this is something that you don't have to have a notion of an application for it. You can just study it because it's just pure abstraction. So as people still do today, we get treated rudely by others. So people of his time in Samos were also rude. Then Plato and Aristotle, of course, were two seminal figures in this. Plato wanted to formalize, create a kind of formal body of knowledge, and the reality with science, scientific thought is seeking, must be expressible in mathematical terms. Mathematics being the most precise and definite kind of thinking of which we're capable. And this was actually a program that was kind of brought to life by Aristotle. And the culmination of this was Euclid's The Elements, and in particular in geometry, he introduced this idea of doing axiomatic proof, and these are the 5 postulates out there. So this one actually I found a little interesting. So this is the Pons Asinorum. So this is the idea that if you have an isosceles triangle, that's the sides say AB and AC are equal, the angle ABC and angle ACB are equal. Okay. So the way Euclid proved this is by basically extending AB to AD and AC to AE, such that AD is equal to AE, and then drawing these these lines across, so BE and CD, and then showing that these two triangles are equal. The ACD and ABE are equal. So again, by side angle side, you can say that they are equal. And then once you have that, then these two triangles become equal. So DBC and EBC become equal. So that's done. Then once you have that, you know that these two angles are equal. So because you're kind of subtracting them off this, you're subtracting equal angles from an equal angle, and so what's left is equal. So that's the argument out there. And then so there's this Lewis Carroll who discussed this topic. It's proposed to prove the theorem by taking the isosceles triangle, turning it over, and then laying it down again upon itself. So he said, why don't we just take the triangle and flip it, okay, and then say that they're equal because of that. Okay. And so why didn't Euclid do that? So the Euclid, in this fictional thing, says surely that has too much of the Irish bull about it. So I guess I mean my interpretation is that an Irish bull is something that's in two places at the same time. And I guess if you're drunk enough, that's true. So and it reminds one a little too vividly of the man who walked down his own throat to deserve a place in a strictly philosophical treatise. So I suppose its defenders would say that it's conceived to leave a trace of itself behind, and the reverse triangle is laid down on the trace so left. Okay. So again, this is kind of an issue that has modern echoes. So they're trying to prove an equality, but how do you prove an equality when you've removed the very thing that you wanted as your left hand side? Okay. So and also. Euclid was worried that if he talked about flipping something and so on, that would bring in more advanced concepts into this thinking that you didn't need. And so he did this proof without resorting to that. So in terms of the mechanization of reasoning, actually, again, there were some very early echoes already in the, I guess that would be the 13th century, is it? The Ramon Llull talked of reducing all knowledge to first principles and developed a kind of symbolic notation and a reasoning machine. So he was a kind of religious guy, and when he tried to bring formalization to religion, the Pope said, "That's where I draw the line. So you can't do this. Don't confuse faith and religion, reason." So Leibniz, of course, was a central figure for us. He spoke most eloquently about formalizing knowledge in this unified language. and actually, being able to turn a crank so that, we can actually resolve disputes. So, in particular, the language should be such that if there was a kind of reasoning error in it, it should look almost like an error of grammar. That's the kind of precision that it should provide. So what must be achieved is in fact this, that every parallelism be recognized as an error of calculation, and every sophism when expressed in this new kind of notation appear as a solecism or barbarism to be corrected easily by the laws of this philosophical grammar. So it should look almost like a grammar error when you've seen that something it just doesn't add up. Once this is done, then when a controversy arises, disputation will no more be needed between two philosophers than between two computers. So computers was actually people who did calculation, human beings who did calculations. It will suffice that pen in hand they sit down to their abacus and calling in a friend if they so wish, say to each other, let us calculate. So then, the formalization actually, didn't happen until the 19th century, particularly with Richard Dedekind, introducing a number of concepts that allow us to kind of reason formally about numbers, and piano arithmetic that actually builds on Dedekind's ideas. And piano actually introduced the modern notation that we use for many of these symbols. And finally, with Cantor and Zermelo's set theory. So at this point, this would have been the turn of the century, of the 20th century, and set theory essentially came into existence as something that could legitimately serve as a foundation for all of mathematics. With that, we also had a kind of study of logic for its own sake, as a formal system of rules that was kind of devoid of any specific interpretation. And Frege actually first introduced this predicate calculus style system, and then Russell and Whitehead tried to fix a few problems in it by introducing a type hierarchy. So this is actually what they had is a very convoluted hierarchy. So the idea is that you have just the nullity predicate, okay, just the truth values, and then you have the type system is basically consisting of the m tuples out here. But the m tuples have these, each of these things has a superscript that actually bounds the kinds of things you can quantify over. And so it's a really difficult system to use because it has both the kind of a type hierarchy and an order that tells you what the concepts can quantify over. So this was simplified later by Church, and but for that Principia system itself, Kurt Gödel proved some pretty dramatic theorems. First of all, he proved that first order logic was complete. That is, every validity in fact had a proof in it. But then he showed that when you actually try to bring in non-logical concepts into that you expect to have a fixed meaning, then the system becomes incomplete. That is, there are true statements about numbers that you will not be able to prove. No matter how you formalize it, there will be some true statement that you won't be able to prove. And one such statement is the consistency of the system itself. So if the system is consistent, it cannot prove its own consistency. So Church introduced the lambda calculus and used it to show that the first order logic itself was was an unsolvable problem, and introduced this Church's thesis that this is really the limit of what is mechanizable. He also introduced the simple type theory. So he removed all the stuff about levels and so on, and just brought in the simple hierarchy of individuals and propositions. And if you have a type A arrow B, then it's at level n plus 1 if A is at level n and B is at most level n plus 1. So you can just create a hierarchy where you have these individuals and propositions, maps from individuals to propositions, individuals to individuals, maps from those maps to other maps, and so on. And a little bit after that, Turing also showed that the unsolvability of the Unscheidungs problem, that you can't show the validity of sentences in first order logic through by mechanical means, and he used this formalization of Turing machines in order to do that, and particularly showed that there is such a thing as a universal Turing machine, and there is no Turing machine that given another Turing machine and an input for that machine will tell you whether the machine halts or diverges. Okay, so that's another unsolvable problem. So this kind of Turing's ideas actually led to the modern stored program computer, and one of the as soon as these things came into existence, Martin Davis actually programmed a Pressburger arithmetic decision procedure, and so he said its great triumph is to prove that the sum of two even numbers is even. I thought that was pretty good for 1954. Then in the 60s, actually, a number of people started talking about proof checking as such. And John McCarthy, that quote I had out there was very influential. De Bruyne with his automath system, which he developed over several decades. So one of my professors at Texas was Woody Bledsoe. Woody Bledsoe not only worked on automated theorem proving, but he also did proof checking on the side. He claims to have actually checked, I think, Morse's theory of sets book. So he claims to have done that. Robin Milner was hugely influential. He introduced the LCF style of proof checking. Actually, I think he did that at Stanford, right? He started this work at Stanford when he was visiting McCarthy. My own thesis advisors are Bob Boyer and Jay Moore. So they built a system which we used to call the Boyer-Moore theorem prover, but nowadays it's called ACL2. And by the end of about the 70s, they had actually done a fair number of interesting proofs with that already. Then when they moved to Texas, they did actually this remarkable thing. They sat down one night and did the proof of the encoding, decoding, encryption, decryption of the RSA algorithm. So they did that basically in one sitting. I did the Church-Rosser theorem in one sitting. So already in the 80s, it was possible to do quite a bit with the technology that was there. So ACL2, the system has been developed since. It started in Edinburgh, and then it's been in continuous development for all these, I guess, 40-something years. So it's a very simple system. It's a quantifier-free, recursive arithmetic style system. So you can, for example, define a function reverse. It says if the list is empty, then just return nil. Otherwise, reverse the rest of the list, and then append it to the first element of the list. Okay, so this is all in list. So you see lots of parentheses. So this is the reverse operation. So it takes a list of the form 1, 2, 3, and then gives you back something in the form 3, 2, 1. And it does this basically by reversing 2, 3 to get 3, 2, and then appending it to the singleton 1. And then you can ask it to prove a theorem like this. So if something is indeed a list, that is, it's nil terminated, then is the reverse of x equal to x? And this is kind of an interesting theorem because it actually needs a second induction. So along the way, it's got to discover that it needs the associativity or append to finish the proof. And the theorem prover that they had in the 70s actually would do that. It would first try to prove it without induction. It would say that's not working out, okay? Because that seems to be a natural thing to want to do. Why do induction unless you need to? And then it would say, okay, that is now how do I do an induction on it? And it would look at this and say, yeah, that looks like a recursive function where I can make use of this thing to do the induction here. And it would actually pick out from the definition the kind of induction it needed to do. So it would know that the induction hypothesis should be on the quitter of x, the tail of x, and it would set up the induction and then expand things so as to do its proof. So that's with this system, many impressive things have been actually achieved with a very high level of mechanization. So there's a whole class of systems that rely on the simple type system judges higher order logic. So Peter Andrews built a theorem proving system called TPS. I think it stands for theorem proving system. So this is again something Peter has been doing for many decades now, already from the 1970s. Then in around 1981 or 2, I guess, Mike Gordon started the Hall effort, and so this again, Mike made very persuasive arguments for why this was a good logical system to use for formalizing. Actually, in those days, he was thinking about hardware correctness, but it's proved useful for a lot more than hardware correctness as well. And actually, higher order logic is a very tiny foundation to build on. It turns out, it's just Zermelo set theory. So the set theory that I showed earlier, and yet, it's able to capture most of what we consider everyday mathematics. So it's adequate to do that. This is one of the kind of abiding mysteries, I guess, is why such a small foundation is actually good enough for a lot of mathematics. So in PBS, we again, built on top of higher order logic. There was a previous system at SRI that was done simultaneously with Hall called EHDM. So, but what we did is we added kind of subtyping and dependent typing to it. So you can have things, types that are things like primes and continuity preserving operations and so on. And you can have dependent versions of these like finite sequences and so on. So you make use of proof obligation generation to catch the mistake. So if you were, for example, expecting an even number and you're given k plus 1, you'd be required to prove that, for example, k is an odd number. And so this, not only does it catch a lot of errors, but it has the, when you look at a textbook or an informal presentation, many of these subtyping and dependent typing constraints are actually what you see in the textbook formulation. So it has the, when you're using it, it feels like a mathematical vernacular. So this is an interesting one. So imagine you have the definition of factorial, and you define, n choose k. Okay, you can not only say that you have an n out there, but again, in the mathematics textbooks, you'll say that k has to be at most n. Okay, so that's captured in that. And then you can say that the result is a positive natural number. That's again, something that you expect to have. But then the right-hand side happens to be this particular fraction. Okay, and again, this is a point where the textbooks fail you. They don't argue that in fact, that fraction is in fact a positive natural number. Okay, and this is not innocent. I mean, this is a mistake. Okay, so and books, papers are littered with these kinds of mistakes, and if you're not careful, this is something that will come back and bite you. Another kind of a very, very influential stream of formalization is actually based on what's called Martin-Löf type theory. See, this was already something that De Bruyne created in the 70s. So actually, I think he preceded Martin-Löf on this. But Martin-Löf is the one who's actually developed a whole ideology around this, and it's based on what's called the Curry-Howard isomorphism, where you view types as the propositions and their inhabitants, the things that are terms of the type, as proofs. So, for example, you can think of the lambda x a b as being something that takes a proof of A and transforms it into a proof of B. So you can then say that that's how you get a proof of an implication. And then if someone actually gives you a proof of A, then you can apply the lambda to it and get a proof of B. So it gives you a way of actually building, applying a modus ponens rule. And you can actually lift it to quantification, where if you make the type dependent, so you have a pi operator out there and you have a B that depends on X, then you can actually have, that's a typo out there, that capital B should be a B of X. So in both instances. So then you can actually have the universal quantification also handled in this way. So the idea then is that you see these types as formulas, and you see their inhabitants as proofs. And in Coq, which is the most powerful of these systems, you can have terms, of course, can be applied to other terms, like lambda abstraction, but terms can be polymorphic as well. They can be applied to other types. And types themselves can depend on terms, as we saw with the dependent typing. And you can have types that can depend on types themselves, so to give you type constructors. Now, in modern enough type theory, you had these pi and sigma types. But there was, for each type, there was a kind of identity type, something that would be the judgment of equalities of elements between those types. And the system itself didn't, even though it gave you a computational interpretation for implication, conjunction, disjunction, and all that, it kind of punted on equality. So it didn't actually specify a computational interpretation. And this is where the homotopy interpretation, you can view types as topological spaces, a term as a point. The identity proofs are essentially paths, and then you can have the identity of those paths as homotopies and so on. So it gives you a kind of much more refined computational interpretation. And this goes back to this Euclid thing, actually. So the equality proof that Euclid actually gives out there is in this sense a kind of path, that shows you why those two angles are the same. So it gives you these increasingly refined notions of things where you just say there's one equality proof. If you go back to this model of style interpretation, then you can have propositions which have a unique equality proof, sets which have equality proofs that are the equality proofs are unique, and so on. So you can carry that, and the univalence axiom on top, that asserting that isomorphic types are equal. So the themes, now going beyond all the different ways, styles of formalization, what difference does it make? It's not something that we discuss out here. Is that where's the time? How are we doing time-wise? Oh, there, yeah, you're doing well. Is that you're going to build up, big libraries, and many of these systems actually have very large libraries. MISA has got a shelf full of these journals of formalized mathematics. Isabel, again has a very large archive of formal proofs. ACL2 has these things called books. So so when you use these systems, what you find is that formalization can be it can go from being a routine activity to being a fairly challenging activity. Actually, it's if you think somehow that formalization just is something that we mathematicians have worked it out, and you just need to be the scribe. You just need to type it to something. That's not true. Okay, there's actually quite a lot of creative effort involved in formalizing informal ideas, and it's really God's work. People who do it know that it is intellectually demanding to do this work. But and it can vary in efficiency. So some days or some pieces of mathematics you can do maybe a page a day. I remember once Larry Paulson telling me there was this proof I'm doing where it took me a whole day to get to the first comma in the sentence. It's just one sentence. So and then the next day he did the rest of the sentence. So that can be how succinct mathematics is, and we've developed a lot of linguistic machinery to talk about mathematics in this very concise and powerful way, and formalizing it sometimes you need to disentangle all those encodings in order to get at the underlying steps. And again, when you've done this, sometimes you think, I could look it up in the library, but the hell with it, it's just easier to prove that damn thing again. So finding things in a library is actually very challenging. Again, because it's kept under a thicket of symbols. Actually, finding things in a book is not so easy either. So it's and as reviewers, for us, it's really painful because I don't know if you try reading Kleeny's Introduction to Mathematics. He has this look up some dagger 35 or something like that, and you look up, you got to keep flipping pages back and forth in order to follow the text. But again, these libraries, I think we should think of as the architectural monuments that we're building in this work, and we should, I think, spend a lot of effort making sure that they are done as beautifully as possible, that we iterate on them very often, and that that they have everything in the form that we'd like to use. And this is actually one of the biggest stumbling blocks. If you look at what prevents us from doing cutting edge mathematics, it's the absence of libraries. If we had libraries, it would be probably a big step towards getting mathematicians to actually sit down and do their work. The other kind of thing that theme in this is the standardized notations. These are really useful. So for theorem provers, people have TP. Everyone kind of puts the problem into that form. The different theorem provers get to crunch away on it. You can actually figure out which theorem prover works best for you. For SMT solvers, SMT lib works that way. For SAT solvers, there's a Dimax representation and so on. So these standardized notations are actually quite helpful. And there's, Michael Kohlhaas, I think he'll be here. He has this thing called OM.doc, which he's using to actually capture a number of different formal languages. I think computer algebra systems have been, among the success stories of this. So these are things where, something like Mathematica, but others are Maple and Axiom and so on, Reduce. These are things which actually mathematicians find really helpful because they provide a kind of complementary thing. They do computations that for the mathematician would otherwise be quite tedious. So, things like putting an expression into normal form, factorizing polynomials, computing integrals and derivatives, solving differential equations, doing optimization problems, quantifier elimination. So these are things that are built into these systems. Now, the problem with many of the computer algebra systems is that these are often not sound. Often they're missing side conditions that you can't apply it to something that isn't differentiable, for instance, and things like that are side conditions that are often not checked. But the typical usage is as a mathematician who knows what they're doing, and they just need the calculation done. So they're willing to take responsibility for the misuse of the computer algebra system. But this is a kind of subtle point that the computer algebra systems are not based on any kind of formal foundation. They do have very advanced algorithms that mathematicians find useful. So more recently, SAT solvers, when people have been working on for more than 60 years, but they've been kind of coming into use for mathematical problems. Sorry, that's a typo. That should be 2. So the ideas in SAT solving actually go back to Davis and Putnam in 1960, and the modern SAT solvers are built on this idea of a conflict-directed clause learning thing. That is, you try and guess a satisfying assignment, and when that turns out not to work as a satisfying assignment, that is, there is a constraint, it doesn't seem to satisfy, then what you do is you try and learn some new information so that you can redirect your search elsewhere. You don't come back down this path ever again. And so the SAT solvers modern SAT solvers are very powerful because of this clause learning capability. So in 2016, actually, this was used to solve a significant open problem. Actually, this was one that was worth $100. So Ron Graham had a $100 reward for even doing this. So the Boolean Pythagorean triples problem, that there is, if you look at the Pythagorean triples of the form a squared plus b squared equals c squared among the integers, then and you color the numbers, then you want it to be the case that you have it kind of two-colored. You want to be able to two-color it. So at least one of these should be blue, another one should be red among the A, B, and C. That'll always be the case. So this thing actually he showed that in the case of 784 it's possible, okay, to keep things monochromatic, but once you get to 7825 you only get bichromatic triples. And so they knew where to look. It wasn't like they started from 0 and scanned upwards. They knew roughly to look at the 7,000s and 500s and so on. So, but they knew where to look. But this is still a huge problem. I think it took like a couple of days of a parallel sat solver, and it generated this 200 terabyte proof. And they actually have a very efficient checker that they've developed in ACL2 that they use to check the proof of this. So it's and Marijn Heuler, the guy who does this work, has been doing other proofs like this. And more recently, he's been working with Scott Aronson on trying to do the Collat's conjecture. So, does everyone know what Collat's conjecture is? Okay, that's the 3x plus 1 problem, 3n plus 1 problem. So the idea is that if you see something that is an even number, you halve it. Otherwise, if it's an odd number, you take 3n plus 1 and continue. So as far as we know, it always terminates that you eventually hit a power of 2 and then you drop down to 1, and then you terminate. Then you can take these two SMT solvers where you're not just dealing with Boolean constraints, but you're dealing with constraints that come from a theory. So you can have, for example, ordering constraints, arithmetic constraints, counting constraints, arrays, bit vectors, and the combination of these. So you have constraints that are the combination of these. And in doing, say, number theory or combinatorics and so on, these are the kinds of constraints you actually hit in a proof. And they're often, painfully tedious to actually kind of provide steps for. So, SMT solvers can actually discharge these things. And many systems actually, in PVS, we've always been using SMT solvers because the earlier system that we built on was actually just an SMT solver. And but other systems more recently have started using them as well, Daphne and Isabel, for instance. And so this helps you actually jump over large parts of the proof through automation. And again, this is the kind of, we'd like to have this automation be tunable so that, for someone who's kind of used to this and can see that, okay, that makes sense, that makes sense. The automation is very powerful, but somebody who wants to actually have visibility into the smaller steps, we can actually turn the dial down. So resolution has been, one of the earliest ideas. Actually, that Davis-Putnam paper had a kind of Boolean resolution, right? But I mean, people in the 30s already had Boolean resolution. But what Robinson did was he introduced this notion of first-order resolution. So if you have two clauses, so P or gamma and not P or gamma, then you can actually resolve them and get a clause that is gamma or delta, but with the most general unifier of the A's and B's applied to it. And this is kind of, a lot of modern automated theorem provers like Vampire and E and others are actually built on this idea of doing resolution and paramodulation. They are very powerful. They can actually do huge numbers of inferences very rapidly. But they have not turned out to be that helpful as a system. It's not something that we find terribly useful as a system. I mean, there's kind of a few exceptions in certain classes of proofs, especially if you're working with inductive definitions with quantifiers. It turns out these kinds of theorem provers. There's one called Metis actually, which is used in Isabel, for instance. So in many instances, it is useful to have a resolution backend to the proof assistance. But in general, they've been fairly disappointing. But on the other hand, they have kind of delivered surprising results. So Bill McCune actually proved this, all Robbins algebras are Boolean. So he had this idea of something he could do with a theorem prover, and he wrote it down, and literally the theorem prover generated an actually beautiful proof of a 60-year-old open problem.
So I think you wrote twice the same equations.
Oh, did I?
I think I could prove that.
Okay, yeah. Sorry, that's, I'll fix that in the slides. Yeah, this is
So what The difference?
I'll have to look it up. So, okay, I'll write the, is there a medium to write with?
Yes, chalk.
Okay, so that should be. So that's what it's supposed to be. Huntington's equation is supposed to be.
Which is which?
This is Huntington. Okay. Okay, so will mathematicians formalize their arguments? And I think, this has been, perhaps the biggest challenge for those of us working in the field. I mean, the technology has been ready, as I said already, from the late 1970s, early 1980s. This is not something where I think the technology has actually been a bottleneck. The libraries have been a bottleneck. That's been a problem. But more than that is the idea that is this something you want to do? Okay. And for the most part, naturally, those of us who value our intuition, would like to stay close to what we're doing. We'd like to think that when we put our ideas on paper, that's when we actually debugging them. But that's not true. I mean, there are a lot of mistakes. I mean, a lot of things actually escape the review process and so on. And the difficulty itself of the review process has been, I think, getting to some people. And this, quote from Vladimir, I think captures, a kind of more modern, a view of, let's say, a more modern mathematician. But to do the work at the level of rigor and precision I felt was necessary, would take an enormous amount of effort, and would produce a text that would be very difficult to read. And who would ensure that I did not forget something and did not make a mistake, if even the mistakes and much more simple arguments would take years to uncover? I think it was this moment that I largely stopped doing what is called curiosity-driven research and started thinking seriously about the future. I'm hoping that in the Big Proof program we will actually set into play the forces that eventually will make it attractive for mathematicians to formalize their arguments. Okay, so some significant successes like this. This is the proof that George led on the Fight Thompson. This is the excited email, so you can see how big it is. Number of lines, 170,000. Number of definitions, 15,000. Number of theorems, 4,200. Enormous amounts of fun. So. This is a truly staggering achievement. I mean, this is the these are the kind of markers that we need to lay down if we really want to make it so that the technology is something that mathematicians will consider using. The next question is, can we trust automation? So the quote from De Bruyn, actually, De Bruyn wrote this in the notices of the AMS. I had written something and he was actually responding to what I'd written, not in opposition to what I wrote. He just wanted to supplement what I'd written. I think maybe he agreed with what I was saying. So we asked whether this guarantee would be weakened by leaving the mechanical verification to a machine. This is a very reasonable and relevant and important question. It's related to proving the correctness of fairly extensive computer programs and checking the interpretation of the specifications of those programs, and there is more. The hardware, the operating system, have to be inspected thoroughly, as well as the syntax, the semantics, and the compiler of the programming language. And even if all this would be covered to satisfaction, there is the fear that a computer might make errors without indicating them by total breakdown. I do not see how we can ever get to an absolute guarantee. But one has to admit that compared to human mechanical verification, computers are superior in every respect. So, this is still important. I mean, even if there's, bugs and mistakes and so on, the complementary force of having something that's big and powerful and, just totally neutral and relentless, checking your arguments is still very, very helpful. But on the other hand, we've seen some advances. I mean, how light does have a small kernel, and that's again an impressive accomplishment to make something that small. And actually, there have been theorem provers that have been verified down to the model of hardware. So all of those things that DeBron talked about, the operating system compiler, everything is actually part of the stack, all the way down to theorem provers. Again, this is a significant achievement. Actually, there's a proof of the correctness of the KML compiler. So it's a variant of ML that was done with Hall. Again, very significant achievement. I think this is something that is a landmark for us. Another topic is going to be the social platforms. So there's this polymath effort that was set up as a social platform. So that's something that again we'd like to see how we can leverage that, so that we're doing formal proofs with social platforms. And in fact, Tom Hales did exactly that for this Kepler collaboration. He was actually giving out little rewards to people to do parts of the proof, and the Kepler conjecture actually came out of that. I think it just got published last week, right? Kepler conjecture paper, because I saw like news announcements about it, and I think it just got published. But you can see how this is a powerful force, that when E times Zhang did this, infinitely many successive primes that are almost 70 million apart. So it was reduced within less than a year, actually, to 246. And same, this Erdős discrepancy conjecture also relied on things that were actually discussed in the polymath project. So in conclusion, so mathematics is this castle that's built on proof. We'd like to make it so that it's got a strong foundation on proof, that we take advantage of automation, not only to check the correctness, but to do computations with proofs. We can use proofs, we can study them, mine them, extract information from them, we can transform them. So these are all things that we can do with the technology that we have available. And we would like to, I think, make it so that this technology plays a kind of creative role in producing new mathematical content. And I think the Newton Institute Big Proof program is an opportunity to really create an inflection point in this technology. So I'm grateful to the Newton Institute, its directors, John Tolan, David Abrahams, and the staff out here for their backing of this effort. I'm really grateful to my fellow organizers, George and Jeremy, and Jay Moore, and Ursula Martin, and Larry Paulson, and Andy Pitts, and Leo Demora, and others, and actually bringing this up. And I'm sitting here as excited as you, looking forward to what will emerge through these next few weeks. Thank you. Questions?
You mentioned teaching as one of the aims of the program, but I didn't see anything in what you said later.
Yeah, so I didn't bring in any specific content on it, but this is actually something people have been doing again for a very long time. So in the 1960s already, Pat Suppies at Stanford had a program of teaching logic and set theory through theorem provers. And then in the late 80s, early 90s, I'd say, Bauweiss and Etchman actually introduced these programs. I think it's called Tasky's World and hyperproof for teaching model theory and proofs using these programs. And actually, I just talked to the person involved in that. They're coming up with new releases now, and this is again an area that I expect will be very active.
I think it's a very important direction, and which is for some reason extremely underdeveloped. But I mean, it should be possible to teach quite elementary how to prove things using proof assistance, and also to teach things like abstract algebra, and that there should be experimental courses of this type appearing in some foreseeable future, I hope, because it's a very important direction.
Absolutely, yeah.
Sorry for
I mean, in other subjects, I think you find a little more of this flavor. I think with mathematics we could make it actually as fun as a video game, and this is what we've actually.
This is my proof with machine gun.
Yeah, that's right. Yeah, first-person shooter.
Blast.
For theorems, yeah. So the when I was with the Texas group doing the work with the ACN2 theorem program and all that. This was we enjoyed this a lot. We just couldn't communicate it to others that this was a lot of fun.
Yeah, so let me mention that. So I've been working on an online introductory textbook with Flores Van Dorn and Robert Lewis, and so we used it last year in an undergraduate introduction to proof, with freshman first-year students, and it worked quite well. It was really meant to be a straightforward introduction to logic and proof, with some components that used interactive theme proving. And it worked, and the students enjoyed it.
I mean, there have been other. I mean, my sons actually, they both one studied in UCLA, did a logic course where they actually had to work with an interactive thing that they've had for a long time there. In UCLA, they have some interactive way of teaching logic. But I think we could actually do a lot more imaginative stuff than that. And I think some of these things like Tarski's world and all that, the idea that you have formulas and correspondence with a blocks world, actually is very helpful because it gives you multiple views on the same ideas. So I think that there is quite a lot.
Well, what I wanted to say is I'm hoping that over the course of the next 6 weeks, over the course of the program, that we'll spend some time talking about pragmatics. So formal verification has taken a foothold in computer science. And, people can get jobs doing formal verification. But for those of us who are training students, who are looking for jobs in mathematics, it's concerning that nobody ever, no matter, math departments will advertise we're looking for somebody who does number theory or algebraic topology. Nobody ever says we're looking for somebody who uses formal methods or formal theorem proving. It's a hard sell to mathematicians because most don't feel that, they've been trained a certain way, and most don't feel that there's this really terribly pressing need. So when you say to them, look, if you spend a few months of your life and you learn some logic and you learn all this funny notation and so on, then you work at it for a few weeks, you can prove that there are infinitely many primes. That doesn't get them very excited. And then you tell them, okay, and then if you spend another, 6 months of your life, you work really, really hard, you can start proving trivial things in your field.
Well, this is where I think libraries will help.
But there are fairly substantial libraries out there, and it's still a lot more.
It is, yeah, that's right. It may not necessarily find a home in math departments. I mean, I think the computer science departments are still the most hospitable venue for this.
But that said, I think there are pockets. So what I want to suggest is that we have to actually proactively. Look, in the long run, I'm sure we'll get there. Whether it's 20 years, 200 years. Eventually we'll be there. But in the short run, I think pragmatically we have to look for pockets of mathematics where it really is a win. So, for example, there are branches of mathematics where the proofs are very fiddly and technical and calculational, and when they're done by hand. And there you can make a case that having a computer check the steps is helpful. There are other parts of mathematics where the proofs rely on computation, and there are concerns about the computation. So, like as with and there you can point to. So I think we have to be clever. I think we have to actively look for those parts of mathematics.
Actually, the other hope I have is that we'll kind of work in pairs. that there'll be a mathematician doing the kind of thinking and the breakthrough ideas and things like that, and then there'll be just like an extreme programming kind of thing. There'll be another one who's checking the results and saying that doesn't work. Have you thought of this?
Maybe that's one possible.
So and if someone who's using the proof assistant was really an expert at it, for them it
But
would be-
so you have to make the case that assistant who is checking is really necessary.
Yeah.
You have to convince.
That's right. I mean, one way that might happen is that if you can kind of bypass a lot of the refereeing process by virtue of having a certified argument, then that might actually be an incentive. George, do you have something to add?
I was going to point out that the reason the theorem proving person is necessary is best evidence is that the mathematician is necessary. That's because so it's all right to have only the theorem prover guys do the formalization if the math is correct enough that whatever problems they find can be resolved by someone without extensive domain knowledge and experience. The minute you start having to work in pair, it's going to be fairly obvious to the person on the other end of the pair that the other guy is needed in both ways. Because the reason the mathematician is needed is because he's getting tons of problems from the
No,
computer
it's clear that the
scientists.
mathematician is needed. We can make the case that the other guy is needed.
No, but I think that this would be, if it led to a kind of better productivity, I think that this could well end up happening. I mean, then maybe we should actually write a grant and do this experiment. Okay, this is something that we could do.
Do you think that these systems will change the nature of what we consider a proof? I mean, it's perfectly possible that we'll produce proofs that we can't understand.
Right. So there's actually already this book by Donald McKenzie on this, Mechanizing Mathematics, about. Mike knows this quite well. So this is stuff that actually happened in the 80s, and there was a court case about, is this a proof? And luckily it never got resolved. Actually, they settled out of court. Otherwise, we'd have a legal precedent. That is not a proof.
Well,
Three people, a mathematician, a computer scientist, and a lawyer is what we need all
Yeah.
together.
What was the case? What was the story? Somebody was suing?
Mike, can you tell us?
It was to do with a verified chip, microprocessor. And the people selling it claimed it was the world's first fully verified microprocessor. But there are several articles published arguing about the nature of proof and the fact that you couldn't fully verify a microprocessor because you'd have to verify stuff to do with quantum mechanics, for example, if you went down low enough. Also, the proof itself had gaps in it. So I don't think there was a very subtle philosophical issue that the lawyers could have got their teeth into. It was just over-claiming advertising. But it did raise the issue of what is a complete proof of something like a microprocessor, given that it lives in a world of physics.
I mean, and this is why I go back to this idea that we deal in abstraction. And I'm actually I'm a formal relativist. I don't. You write down some axioms, you do some proofs, and whatever. If those axioms turn out to be inconsistent, well, too bad. Okay. if they turn out to be uninteresting, well, too bad also. So I think a lot of these things you just have to start at some level of abstraction and say, this is what I work from. And actually, I think they're very interesting. challenge is even in finding what their abstraction is. And if you actually try to formalize Euclid, what kinds of things do you have to put in there into your formal system to capture those arguments? So I think that there's a lot of work to be done there. So you don't have to, all you have to do is say that you created a kind of an abstract body of knowledge and claims. You don't have to make the leap to saying something concrete is correct. So, but going beyond that, I think another thing it will do is that with the technology you can actually, you can probe the proof in various ways as well. I mean, that's something that you can't do once it's kind of put down in text. Whereas if with something that's available, you could say, oh, that stuff is automated, but I really want to see what the argument is. I'd like to see the details. I mean, you may have some particular reason for doing this. Maybe you want to extract some numbers out of it and so on. So, having the proof as itself a mathematical object actually has many such virtues. It doesn't necessarily mean that the proofs that you develop, with mechanization are necessarily, more comprehensible or less comprehensible. I think that's another dimension that you have to worry about. I mean, if you want to, be useful in education, for instance, maybe you should give the possibility of actually generating proofs that correspond to clever explanations. So going back to this card trick, did people figure out the proof? Okay, so it actually has a very simple argument. So, I laid down the things one by one, but actually you need to have done any of that. Imagine the cards are arranged in a circular deck, okay? Then what is going on is that cut is just some point in that circular deck. And the top 4 cards are going to come from either side of that cut. There's just shuffled versions of things from either side of that cut. So naturally, if you take 4 consecutive cards from around the cut, they're going to be a matched pair. And then when you close the circle after removing those 4 cards, that's going to be a repeating pattern again. So, so you could have actually done the trick a different way. You could have said, now that I've shown you these 4, let's do another cut. I can take 4 from there and let's do another cut. I mean, it's still going to maintain its property. So this is called Gilbert's card trick. So this is a guy who invents card tricks for a living, and so this is Gilbert's card trick. So it's got a simple explanation that is also a proof.
Mm. But has it been formalized?
Yeah.
Yes.
So this
The
might.
thing they did in
Yeah, it's
that's a different
one
one.
of the early things.
The Hewitt did a.
It was one of the.
Yeah. So those are simple versions. Actually, the version I showed you, I've done a formalization. This argument also. So those are that's a simpler version of the problem that an uglier proof and so on.
Of course, if you actually miss the shuffle and alternate between inserting 1 or 2 cards, it doesn't work. So
Yeah.
you have to do
shuffle right.
You have to do a perfect shuffle for it to work.
No, it doesn't have to be a perfect riffle shuffle. It can be any riffle shuffle. So it can be like 1 from here, 3 from there, and so on. It can be any riffle shuffle. It doesn't have to be perfect. But I mean, I can't do a perfect shuffle. I think Percy is the only one who actually does a perfect shuffle. and he's spent a lifetime training himself to do that. Okay, so thanks a lot.